For those who just came in, there's some worksheet on the back of the class. Please take one. Is there anyone who still needs some worksheets? Okay. Go. Anyone needs worksheets? Worksheets? Free to grab. Okay, perfect. Here you go. Worksheet. Sheets. No problem. For those who just came in, there's some class worksheet at the back of the class on the table. Yeah. All right, let's get started. So today we're going to mainly talk about the NVIC. Come on, guys. We're about to start. Okay. So today we're going to continue with what we left from last lecture around the interrupts. We're mainly going to look at the NVIC, the nested vector interrupt controllers, which tells us what do we do when multiple interrupts happening and what happens on the software level as well as on the hardware level. Before we jump into the lecture content, some announcements here. So hope you all have today's lecture worksheet. Please make sure that you put your names, unique ID, and GMID on the top of the top left of the worksheet, and then leave that on the desk while you're exiting the class, the desk at the back of the class. So yeah, please make sure you put the name down. Otherwise, you get the content, but you don't have the participation, which is also okay. So we're going to have midterm coming up next Friday. Exciting time. As we said, it's already posted on the website. So basically, we have three rooms for those. You will be assigned later on by the teaching team which rooms to go to. And then once you're inside, I think we were instructed not to monitor you guys. So yeah, just be wholesome and then finish the work. The topics to cover, it's basically the mainly like the lecture materials until today, basically the interrupts and NVIC. And the interrupts and NVICs are going to be going to be a bit less focused on because it's kind of new, and also some of you guys might have done the lab when the exam happens. Some of you might have not. So it's mainly going to be like multiple choices and like short answers. We're not going to put like one big question over the interrupt or NVIC. And we will post the practice exam tomorrow, Friday. And we will have a review lecture on next Thursday. It's just like one day before the exam, which seems to be the perfect time for everyone to start studying. And if you need any of the SSD accommodations or other accommodations, please come talk to us, because we would have to reserve an additional room with essentially longer reservation for those accommodations. We are aware of, I think, probably 2 students have those accommodation requests, but just to make sure we don't miss anyone. Any questions? Okay, perfect. That's a strong start. So we left with an open question from last lecture. Basically, what if like the processor gets an interrupt while it's doing another interrupt? What if like some interrupts happens to be more important than the others? Like when you say like driving your flight or driving a car, indicator lights might not be as important as your ABS, the emergency brakes. So how does the system deal with all those interrupting events? As well as how do we set up and control those interrupts, either in software level programming or in the hardware levels, in the registers, etc., as you probably would imagine. And what if we are in some kind of critical section of the code that's not supposed to be interrupted? Is there any like protection mechanisms protecting the main program from being disturbed by those hardwired interrupts? So as you would probably guessed by the title of the lecture, it's going to be mostly handled by the NVIC, or nested vector interrupt controllers. It's pretty much like a hardware module in the ARM Cortex processors that manages the interrupts handling, priority levels, and the nested interrupts, as in multiple interrupts happening at the same time. It enables like efficient and also low latency interrupt controls while supporting a lot of the flexible priority schemes. That's very useful for you as a programmer to determine what should happen at essentially what time and what order. So a little bit outline of the lecture. We're going to talk about the interrupt control registers and then the interrupt flow control as like a diagram. And then we're going to go into the priorities to see how do we deal with multiple interrupts with different urgency, so to speak. As well, we're going to have like overlapping interrupts, which it's like the beginning of the question, what if they happen at different time, different cycle? How do we make sure they're pipeline, or how do we make sure they're executed at the correct order? Okay, so let's first go to the interrupt control register. Just like almost everything inside of the Cortex hardware side, it has control register for those interrupt controls. Remember from the previous lectures, ARM gives an architecture that supports up to 256 IRQs, the interrupt requests, and the first 16 are the system exceptions, and the remaining are for like peripherals and external devices, etc. For the STM32, we're working with, unfortunately, 96 plus of those 16 system exceptions. And we will look at these peripheral interrupts, like the first 96 of them, in more detail in next slide. So basically, you're going to have these registers that used to control or used to enable, disable the interrupts, and also to set the priorities. There are 2 ways to do those, like 2 sets of hardware, so to speak, to control those. And it's good to understand that conceptually how they work. They kind of do the same thing. The CMSIS, the top one, it's a software framework that developed by the ARM to simplify the embedded software controls or like interacting with the interrupts. It provides what they call like a hardware abstract layer, HAL. Not sure how many of you guys are familiar with that term. So basically like an interface between the application program to the hardware levels down there. So it's like additional layers for you to easier as a programmers to easier to access. And they also have the device manufacturers registers. Basically each of these peripherals, especially those external ones, chances are they're going to give you the exact address of those registers that enables or disables these controls. You can also directly access through those. But it's likely going to be a little bit faster because you saved one layer of the interface, but you also have the risks that you have to know what you're doing. Otherwise, you're going to mess up with something. It's easier to make errors, as well as, I think mainly for the error probing issue. But both of them are okay. It's essentially two sets of registers that does the same thing. Just depends on which one is easier for you to use. And if we look at the CMSIS first, these are like the functions that embedded inside the ARM that let you to control any of these registers. You don't have to remember name to name which of these are, but it's and it's also probably easier to understand than if we look at them in terms of the registers instead of the functions, which is here. Okay, so these are the actual registers that's within the CMSIS that's used to do what we just described. To start with, we have the ICTR, interrupt control type register. It basically shows the number of interrupt lines that the NVIC supports. In ARM, it's up to 240, and this would be it will be basically hardware dependence. Depends on the exact hardware you're working with. They're going to give you a different number. And more of those you're going to be interacting with, I guess more, is the enable and like the clear enable registers. These just look at the name. Basically, they do the enable and disenabling or like clearing the interrupt. And they have two registers implemented for that. We will touch them in just in the next few slides to show you why they're doing that and how they work in between. One of them, the set enable register, is read and write, and then the clear enable register is generally considered as write only. My bad. I think there's probably a small typo on the website, so bear with us. It's actually write only, generally considered as write only. And the ISPR or ICPR, basically that menu, it's like a pending state register. It sets an interrupt as pending or clears an interrupt from the pending state. And we have the active bit register to identify which interrupt is currently active, as well as the IPR, the priority register that sets the priority of the individual interrupts. Okay, we're going to talk more in detail on this one, but yeah. So these are like the examples for the manufacturers, like the registers that are provided by manufacturers that you can also do or also interact with, doing essentially the same thing as before. They pretty much give you like the address of those and then tells you what are they and what they would do, and then you would just access those memory as if you're doing like a memory I/O write, like a load or store, and then essentially the same method, but it's different in the memory location. Any question? Okay, perfect. So yeah, there are some advantage and disadvantage between them, as we briefly mentioned before. If we use the more ARM provided one, the CMSIS, it's usually easier to read and maintain, and it's portable, compatible across different Cortex-M devices because that's implemented by the ARM. But the disadvantage is basically you have that one additional interface layer, which might slightly increase your code size if that became very important to you. And for the direct register, you have like more controls over specific hardware features and potentially faster to execute because it saves a couple clock cycles. And the disadvantage, as you probably will imagine, is not as compatible with other devices if you want to work with different microcontrollers. Also, it requires deeper understanding. You have to know what you're doing. Okay, so how they lay out inside of this one register? If we're going to use the ISER, the enable register, as an example. So basically, it's hard-coded bit by bit, and one register bit for each of the interrupt index. If you guys recall from the last lecture, each of the interrupt have a index number hard-coded to it. So each of the bits corresponding to one net, and 0 is not enabled, 1 is enabled, etc. And yeah, I think the way they map it, it's pretty much similar to the P address that we talked before. Like within a peripheral, how do we know which registers is enabled or not enabled? You can think of them as similar control mechanism. And we will have multiple of these 32-bit ISERs to accommodate for enough number of the interrupts we have. So for the ones we work with, which is 96, we're gonna have we actually have 3 of those ISERs, the enable registers, to be able to have enough control bit enable bits to map onto each of the interrupts. Okay, so if we take, as we mentioned in the last lecture, like a few slides before, basically we have 2 of those registers, the enable and also the clear enable registers that's controlling one of the each one of the interrupt, and they all do like essentially 1-bit mapping to each of the interrupts. And if you write a 1 to the selecting like the enable register, it basically enables the interrupts and set that bit to 1. And for the write only, the clear enable, you write it 1 into the device, and then the interrupts will be set to, it will set the bit inside of the enable to 0 after that was set inside of the clear. And why are they doing this? Why are they trying to have basically 2 sets of registers doing this control? Any guesses here? Yes.
Because you said it's hot-wired, so maybe it just pulls the signal high. That's all it does.
So it's easier to execute or easier to check, so to speak.
It's also faster?
Yes. So less computation. That's one of the reasons. Yes, definitely. Yep.
Maybe you want to use it as a mistake, like what the inventor is right now for the next.
Like kind of a D flip-flop, you hold the state, and then you have like additional layers of, that's also, I think that's the other main reason as well. So these 2 are the main reasons, I believe. The second is, essentially providing another layer of protections, because these things are, or like another layer of redundant, because these are quite important. And then if, say, some hardware got stuck inside of the enables, it's always set there. And the program might have trouble to access that or write a value to that register. So we have an additional registers, like clear registers, that does that, so that it makes sure every time when this command is happening, it's executed on the hardware level. Okay, just like a quick example here. If we have like 1 set to the enables, that one goes high, and then once the interrupt is finished, and then when that clear happens, the clear 1 high bit will cause the corresponding enable bit to go to 0. It's just like a quick illustration here. Cool. So these are the register for your particular data sheet. You feel free to look at them after class or during the labs. So these are the step pending and the clear pending interrupts. Works similarly to the enable and in terms of the internal mechanism, but it's basically the NVIC saying that, hey, there's like an interrupt here that's pending, or it's pulled high, so to speak. And then your NVIC will go through these pending ones and chose or like look at if this thing is turned to active, to response, or to be executed as the next IRQ, the request. and you will clear the pending bits of that chosen interrupt whenever it starts to, active, or goes to that service route of that interrupt. Yes? No, it will not. It's after you finish that, or after this is being disabled, you put a 1 into the clear, and that 1 will cause the set enable register to become 0, that 1 bit.
So in bit 7, for example, you said that in the set register, you want to set that interrupt to put a 1 in bit 7, for example. That includes what would you?
You mean for the pending or for the enable? Sorry. Okay. This one?
Yeah, because here's like their connection.
Oh yeah, I think, yeah, sorry. The illustration seems to be a little confusing. But yeah, it's like after the 1 is set to the clear, that will automatically set the select register to 0. Yeah. Sorry for that, yeah.
How do you clear the clear register?
How do you clear the clear register? That's actually a good question. You could run 0 to it. It will have no effect, but you just update that bit. Yep. Any other questions before we move on? Okay. So yeah, these are the pending and clear pending interrupts. Basically, when an interrupt is triggered, the hardware sets the pending pins to high, and then you have to manually clear these pending states when you're finishing, when you goes to your ISRs. These things might seem a little bit abstract right now. Later on of the lecture, we will have a diagram that lines each state to each other, so you will have a more overall understanding which register is doing what during a interrupt calls, basically. So this is the interrupt active state register. It indicates which of the interrupts is active. It's read-only, so that we don't mess around with what's happening on the interrupt level. And why do we need this? Because imagine we should already know which interrupts we are in right now, because all those things are hardware wire triggered, all those peripheral ones at least. So why do we still need this register to tell us which one we're in right now? Because as you probably thought about, the interrupts can be interrupted by another interrupt with higher priority. So even though we kind of know which ones are triggered, we still need to know which exact interrupts calls that we're in right now, because chances are they can also have multiple layers. That's why we need this additional active states register for that. Okay, so those are the basic registers that it's going to be quite useful in a normal or simplified case of a interrupt calls. Basically, enable and disable registers, and the pending and clear pending registers to determine which ones are pulled high, essentially, as well as the active register to check which interrupts is currently high, it's currently active. We can also do trigger the interrupts in the software using the software trigger interrupt registers. Those, usually for debug purpose, you have some debug informations there. And those part we were not going to focus too much in our lecture. And the next is for setting the priorities. Basically, it's another register called interrupt priority registers that allow you to set a priority value to each of these interrupts, which we'll talk a little bit more in the next parts of the lecture. So yeah, as we were saying, give you a little bit overall a view of what's happening to each of these register values and at which state. We're going to briefly do some like basic interrupt flow control diagrams here. So this is I believe, one of the simpler case. So basically, the interrupt requests come from the peripherals and then goes to the NVIC, which is that interrupt request up here. It goes high, and then that triggers an interrupt pending state to go high, so that the NVIC identified which interrupts to do and writes a pending flag in the pending register. After that, the process module basically the program will jump from the thread mode, which is like the normal main program, to the handler mode, which is the interrupt mode, or the interrupt service routine. So on the x-axis, which you can't see, but basically it's in terms of the time, and then this is what's going to happen. And then once it go to the handler mode, it pull down the pending state because that one is being activated. Is this clear, or any questions on this? And then later on, we're going to add the active register as well. Okay. So sometimes the pending can be cleared by the pending state can be cleared by software. So it's basically like the software or your program decide that the raised interrupt should not be executed, or it's not important enough given the current circumstances. Then the software would do the clear. In this case, it basically got shut down during the pending states, and the program stayed in the thread mode. And this can happen when the interrupt is not enabled at all. The clear of the pending. That's not dependent on whether the interrupt enable is up or the interrupt request is up or not. Okay. All right. So here we're going to add in the active state register. Basically, as before, we have the interrupt request coming in, which caused the pending to rise up, and then that triggers after the processor mode, or like the core or like the main program goes from the thread mode to the handler mode. It basically indicates it's inside of one of the active interrupt calls. So the active register of that interrupt will be high, and then that also basically this shifting mode in the program here, this triggers the active states to be high, and also, as we showed in last slides, cause the pending mode to go down. And then after that, it's pretty much like what you expected. Whenever it's finished, the active states of that interrupt goes down, and then your program or the core exit from the handler mode back to the thread mode. But those things, these part, however these being like cleared, it could either be software or hardware. These have basically this ping was not controlled or not triggered by the finish of whatever you do in the main, like these signals. Does that make sense? Okay. Okay, good. Okay, let's go a little bit more complicated. So what if the interrupt request is not cleared in this case? Like other things are pretty similar. The interrupt pending goes up and then goes down because the actual processor went to the handler mode already. And yeah, this is actually one of your worksheet questions. You can try to draw what's happening on the bottom three signals if this was happening. And also feel free to discuss with your neighbors. We can do like 3 minutes or so. Yeah, there you go. And please make sure you put your names on it. Whoever doesn't have the problem. Yeah.
Thank you so much.
All right. Okay, do we have some thoughts on this? Okay, do we have some thoughts to it? Anyone wants to share their answers or share some thoughts of their processing? Okay, yeah.
We think it's just business as usual. So pretty much the same as the last slide. There's no I think it'd be a separate signal that will trigger the interrupt request.
So basically like this. So just okay. And why would why wouldn't the interrupt request signal here trigger another pending states to go high?
Because we think it's triggered on the rising edge of the clock. So it stays high.
Anyone else think the same? That is correct. That is correct. However, the answer might not be just like that because there's something else also checking that. Any other thoughts? Yes.
So it can the interrupt active services when it comes to the spread low, but immediately get interrupt again. So it's like a deep down, but without any state.
And why is that? Or does that cause any changes in other signal? For example, the pending or the active?
It would stay low because there's not a rising edge trigger again. But for interrupt, it's still being requested, so it would be
Okay, we're getting closer. That's any other addition? So basically, it's after the first ISR got executed. At the end of that, the program checked one more time to see if the ISR is still high. And that triggers it go back to that register. That is correct. And the previous one, you're also correct. The pending state was not triggered. Okay, I will just give you the answer. Okay. It might be a little bit harder too. Okay, so exactly. So basically, it will go right back to the processor, like the handler mode, because at the end of that, it checks the ISR signal to see it's actually still active. You will see a little bump on the pending, but you're very right. That was not caused by the interrupt request. It's caused by the checking to see that's it's still active, so it got pulled up by the processor, and then that little bump got quickly shut down because that goes to the active state of that interrupt. And then, so you just see a little of this bump here. Does that make sense to everyone? Okay. Okay, perfect. But yeah, great. I think everyone answers it are correct, which is super nice. Okay. Cool. How about this one? So what if the peripherals are going like super fast, those requests? Say we have, instead of here, the pending state actually lasts for at least 3 times of the interrupt request signal. What's going to happen to the these two later signal? What happens? Okay, this is also on your worksheet, and yeah, let's spend another 1 minute or 2 on it. Feel free to discuss with your neighbors. All right. Any thoughts on this? What happened to the active state and the processor mode? Any thoughts? Yes, back. So we have one thought on it's basically going to just stay as if there were only one interrupt request sent out, and then these two registers going to basically act as somewhere after the pending is down. This one goes high, and then the processor goes from the thread to handler. Is that anyone? Any other thoughts, or anyone agree with this? Any other thoughts? Everyone agree with this? We have an unanimously correct answer. That is correct. So basically, yeah, exactly like you said, because you haven't even go back from the, got turned down from the pending state. That multiple triggers actually be treated as one trigger, and that enables the active states, interrupt active states, that goes high, which cause the pendings goes down, and then the processor, does the normal thing, doing the handler mode, and after it exits it look back one more time, everything looks fine, nothing is happening, so we just comfortably go back to the main program. Okay, cool. No questions? Okay, questions.
Yeah, I'm a little confused for the processor mode. It seems to start going up before the falling edge of the interrupt pending status. Why is that? Sort of what triggers it for the processor mode to start going from, I guess, red mode to engage mode?
You mean like the beginning of here?
Yeah. What triggers that?
The triggering of that is, so the triggering was that is the essentially the pending states actually. So here is what triggered this thing, but it takes a little bit of time for it to actually react to this pending. So basically, if you think back, normally we have to finish the current instruction before we can do the interrupt. So basically, whenever the pending's up, the processor got noticed, I'm supposed to do something soon. And then after it gets to do that pulls down the pending and also pulls up the active. These two things essentially happen at the same time.
So are you just saying the rising edge of the interrupt pending status is what triggers the start of the processor mode to go up?
Sorry, which one? Sorry.
Are you saying the rising edge of the interrupt pending status causes the processor mode to go up? It just takes.
Yes, it takes longer.
In the previous question, it seemed like the difference between the rising edge of the interrupt pending status and when the processor mode started increasing was much shorter.
Yes, that is because we kind of want you to take in consider that this whole pending state takes longer than a multiple interrupts request here. So it's a cooked question for you, but it does happen in real time, in real life. Just this is so that we can have you look at the interrupt pending signal, the state, that covers more than one rising edge of the request. And the reason it takes longer than that is because the processor is taking longer to actually enter in the handler mode.
Yeah, I understand why the interrupt pending status is so long, but is the processor mode changing triggered by the rising edge of the pending status, or no?
It is.
So then,
You just take the processor longer to be able to actually go to that handler mode. Yeah, imagine if in previous if say this rising edge just goes down here, then the processor mode is probably going to rise up somewhere here. instead of go all the way back to here. Hope that's clear. So yeah, this is, okay, let's do one more. So what if the interrupt request, the IRS goes high again? What happened to the remaining 3 of them? You know, before it goes high again, before the processor comes back from the handler mode, also the interrupt active is still high, but the pending is already down because, you know, the processor already went to this handler mode. Okay. Yeah, let's take another 2 minutes.
It would go, yeah. She'll try going down, but then seems to fall again, she doesn't. Yeah.
All right. Any thoughts? Who wants to share some thoughts? Okay, I'm going to ask someone else, but thank you. Anyone else? Anyone around this crowd? Yes.
Does the handlers already active? I assume they do similar things where it went up a little bit and then the active status would flip down and then the processor mode would also go another flip.
So basically the handler mode goes back a little bit and then go back to the handler mode, and then the interrupt active states go down a little bit and then go back. What about the pending state?
I think pending would go up, but just for a short period.
Shorter period of time and goes down again. And then see. That's some good thinking, actually. Anyone agree or disagree with that? So basically, you're saying the this new I guess positive edge, the rising edge, caused the pending states to go up, right? And then that was stay up until this handler mode go back to the thread mode, and then look at it again, and good God, it happened again, and then it goes right back to the handler mode, as well as the active. It goes down a little bit and then goes right back. And after that, the pending states goes down, right? That's anyone agreeing or disagreeing with that? Any other thoughts? Okay, I see some thumbs. Anyone who disagree with it? Okay. Okay, so that is actually correct. So yeah, good job. So essentially, the even during like the processing or like the handler mode of the processor, the rising edge of the interrupt request can still cause the pending to go up. So that essentially let the processor know that there's something still trying to be executed, even if it's from the same interrupt. And after the processor finished the handler mode, it look it again. Oh, there's something pending, and go right back, as well as cause the active states to go right back as well. So this looks similar to what we had, like I guess at the first lecture worksheet, but the cause of the pending states was different. This one, the pending states, was caused or like pulled up normally as normally would be done, which is caused by the rising edge of the interrupt request. Are we clear on these? Any questions? Okay, yes. Go back to what? That's a very good question. So we will see in more detail in the next few slides. So what it actually doesn't really go back to thread mode. And then you will see those, I'm glad you asked that question actually. The slope here, not sure if you still remember from last lecture, the whole stacking on stacking things. So basically, a part of those slow rising slope was corresponding to the processor trying to do save everything inside of the current process. So what that dip essentially means is it's trying to do the unstack and then realize that I should probably not do that yet because there's something else happened. So it goes right back. Yeah, that's a very good question. Any other questions? Okay, perfect. Cool. So next we will talk about like the interrupt priorities, how exactly we set the priorities of each of these interrupts. Previously, we only look at the cases where there's only one interrupt, although it can be triggered or happen at a different time. But the next few slides, we'll be looking at how do we handle when we have multiple interrupts. Okay, so basically, okay, let me just put everything here. Okay, yeah, basically the ARM lets you to set the priorities as you want, especially on like the peripherals level, which peripherals or which interrupts has different priority. And essentially higher important, like more important can be amped lower important interrupts. So if you have like lower interrupts trying to executing something more urgent happen, that can jeopardize that, basically. The higher one goes first. And then we're using what they call like a gulf scaling. I'm not super familiar with the term, but basically the lower number means higher priority. Any guesses on why we're using that? So essentially each of the interrupts or peripherals in this case has a priority number, and then the lower the number is, the higher the priority it is, and why we're using this gulf scoring. Yes. Exactly. That is, yeah, exactly. Because we don't really know what's the, across different types of microcontrollers, even if they're all under the ARM, where it's kind of hard to set a highest absolute value there to be the high, because we don't know in this set of hardware what's the amount of interrupts it has, etc. So we just chose the lower number is that it's a higher priority. And those are essentially like the priority level registers are put at those memory addresses in the chips that we're working with, the Cortex-M4. So you notice that they start with E something, so it's pretty far up there. Not sure if you remember the figure from the MMIO. Those things are essentially at the top, which is the system memories, is where are all these things stored. Okay, so quick example here. So we have the interrupt A that has the priority number of 5, and then we have the interrupt B that have the priority of the 2, number of 2. So the B have a higher importance than A, and then that would, if they both add the pending, then the B will be executed first. And there are some, hard-coded higher, well, so to speak, yeah, like there are some priority levels that you're not able to overwrite. Essentially, for example, this reset and MI, non-maskable interrupts, as well as the hard fault. They are set to have like a higher priority number in terms of negative value, so that there's no way that your positive value or 0 can surpass that. Those are, so the NMI, as a quick reminder, they basically, it's something corresponding to critical events that require the immediate attention. So that usually corresponding to like hardware failures or system failures. The reset, which you probably press it a lot during your lab, the reset button kind of have the highest priority that cuts down everything and reset or reboot the system back to the beginning. And hard fault, it's basically exceptional error condition that cannot be handled by other handlers. For example, the ones that if you do like divided by 0 or like trying to access an invalid memory address or like stack overflow, etc., those ones are handled by the hard fault. So that's like the third highest priority. Yeah, but you're able to adjust any other interrupts, which is a lot of power to do. So yeah, this is the mechanism used to change them. They are configured by what we call the interrupt priority register, IP or IPR. Each of the priority consists of 2 fields. One is called preempt priority number and the sub priority number. The first number basically corresponding to the priority of this interrupts across or which type of or which level this priority is. And the second, the sub priority number means within this level of priority, which index or which order this one is currently at. So we have those 2 numbers that's controlling the corresponding priority. And we have like 1 priority byte for that, so 8 bits in total. We actually not only going to use the top 4 bits for that. So by default, it's set to be 2 bit per priority. The first 2 bit for the preemption number, and the second set would be the sub priority number. However, we do have more controls over that. You can kind of determine your own configurations within these 4 bits. You can set 0 bits to be the preemption priority, and then all 4 bits goes to the subgroup priority. Just depends on your own configurations. So in total, you could have different, basically 16 levels of priority. Any questions on this so far? Okay. And the reason that we kind of use the top 4 bits here is kind of like a historical reason. At the beginning, like the Cortex M0, M1, etc., they chose the top 2 bits, and then M3, I believe, top 3 bits or something. And then M4, M7 became the top 4 bits. They kind of just keep using the top bits so that all the programs that you wrote with the later, more current architecture can still go back to the previous easily. Otherwise, you might cause some issue of the compatibility. All right. So yeah, because these things, as you're probably going to imagine, are quite important, because if you set the bits distribution, or like 2 bits, and then change to say like 3 bit, 1 bit, those things are going to change the program or change the whole processor behavior quite dramatically if there's an interrupts happening. So these things are a little bit trickier to config. Every time you have to basically access and set those configuration bit to like a key first. for example, you can read it after. Basically, you have to write a certain value to a key field before you can config the priority bits configuration. Otherwise, it's just going to be ignored. Okay, so this is what it essentially looks like, the interrupt priority register in ARM Cortex-M, and they are implemented per interrupt. So each interrupt have its own interrupt priority register, or IPR, and inside of the NVIC. So if you look at each of them have one, and they're all 8-bit. And then we'll be setting that based on the interrupt number, which is here. Each interrupt also have its own corresponding index. Okay, so for the system interrupts, the software exceptions, etc., they have their own priority sets. Some of them you can remax their priorities. Some of them you can't, as the three ones that you count, we showed it before. Others, you still have the capability. For some of them, you can change their priority values, etc. Just like the other interrupt just like the IPRs for the peripherals that we just showed. And so generally speaking, in embedded systems, we often have to perform some critical operations, and in which data should not be corrupted by any other interrupts, which is what we showed at the beginning of the class. What if the code, or what if your program is kind of inside of a critical block of operations, right? You don't want some less priority or random interrupts to jump in and breaks your own program at the moment, which is what this register, or base PRI, comes handy. It's called base priority mask register. Basically, it's used to achieve the protection of these critical part of the code. It works so by essentially set a number of it takes the input of a priority level, and then it basically tells the whole system, in this case, that anything that the priority level goes below than that, or the number is higher or equal or higher to that, will be ignored during this period of time. And then, which is essentially what this function here does, is says anything that's 5 and above in terms of the priority value will be ignored in this block of code. And then after that, you should probably do something, set it back to 0, so that it's open for all the it opens back to all the interruptions. There are some other similar exception masking registers that you can also do this thing called prime mask, for example. It basically is a little bit stronger, or it's more powerful than that. It basically disables all the exceptions except the 3 that's non-maskable ones we mentioned before. And we also have the fault masks. So it set the priority level to -1. So even the hard fault handler is blocked. So essentially, only the reset and the really critical NMI interrupts will be able to interrupt whatever you're doing here. So these things just give you different levels of controls on how critical this block code, or trying to protect your main program from being interrupted. And in case you're wondering, this MSR command here in assembly basically means move to special register. That's an instruction in ARM that dedicated for moving value from normal registers to a special register, like controls, etc. Okay, perfect. Yeah. Any questions on these? I hope these are more or less straightforward. That kind of protects the core of your code. Okay, beautiful. All right, so next we're going to go through some examples and hope these will make whatever we just talked about in abstract makes more sense to you. Like at each stage, what's happening if we have like multiple interrupts happening. So let's start with a single interrupt. Basically, in the graph, you will see we have things laid out for you on hardware line here, software line here, showing you what's happening on the program level or the hardware register, for example, register level. And then we also show you the program stack in case you want to store something when you go from the thread mode to ender mode. And then we also put the priority table here. Here we only look at the interrupt 0 to 4, and each of them have one bit corresponding to its pending state, as well as enable and active. So we start with the all of them being enabled, meaning they're all able to raise a request. And the base priority here is set to 256. Reason for that is, that's what the ARM architecture gives us, and that's like the least priority you could have inside of any ARM systems. We just set that as the base priority so that any interrupt that's happened will be able to interrupt the current program. So this is the beginning of does this setup make sense to everyone? Okay, perfect. So something interesting happened. We're gonna have a interrupt. The interrupt request RQ number 4 happened and becomes high. So the corresponding bit here in the pending goes to 1, indicating something is happening, it requires some attention, and then it would do the in the hardware level, the program will basically stack all those registers that's needed to keep the current stat of the program into the stack. R0 to R3, R12, link register, etc. And then it will goes to the actual execution of that request, goes to its subroutine calls, basically. And then that caused the pending to go back to 0, and then the active go to 1 because it's currently active. And the base priority is set to 6, which is what we had here. The priority being set for the number 4 is 6. So that at this stage, anything that's less priority than this will not be able to interrupt this interrupt. So yeah, after that, we basically, we had done everything, and then we branch out this. We go back to the previous main program, and when this happens, remember like the link register at the time have like a special value that tells which pointer, like stack pointer is using, and then that kind of help you to know where to look at in the memory, and then unstack all those previously stored value. And then after that, which is unstack process, unstack stage. And at that time, the active also being put to low, indicating that it's already finished. We're not doing any of this interrupt at the moment. And we get out of it, back to the normal process, main program, and then the base priority get back to the 256. Does this, okay, I already see hands. Yes?
How do we know which priority to go back?
How do we know which priority to go back to? So that's a very good question. So if we have other things line up with a higher priority, then we use that number. If we don't, we just use, if there's nothing ongoing, we use the 256, which is the lowest priority possible inside of this program. Otherwise, unless otherwise specified by the main program. Any other questions? Alrighty, perfect. So, okay. Then we're going to be a little bit more complicated case here. Yeah. So what happens if like a higher interrupt occurs while the CPU is, or like the processor is still handling other interrupt with lower priorities, right? So basically, long story short, the new interrupt will interrupt the current ISRs, the subroutine, like the service routine calls, and then we'll push a new ISR stack on the stack. Let me show you again on the graph here. So say we in the middle of executing the RQ4, the interrupt request number 4, we have the base priority of 6, right? And correspondingly, the number 4 is also on the active bit here, which is high. Can you see my? Okay, perfect. And then, yeah, the number 3 goes to pending, is rising, you know, a interrupt request, and then it happens to have higher priorities than the current number 4 because it has a priority level of 3. Okay, it's a little bit confusing, but they're not correspondent. But just happens to have like higher priority at this interrupt request. And then what we're gonna do, we're gonna just stack whatever we have with the RQ4 into the stack. Just the same or like very similar to what we did when we were at the main program. We just say exactly the same thing to the stack again. And then we pull that pending bit down and then put that active bit on because we are essentially going to the interrupt request number 3. Notice that we have like 2 active bits on the interrupts, which is okay in this case. And then we set the base priority to 3. Now that's higher priority than the priority 3 are able to interrupt with these interrupts. Okay, I feel like I'm using the word interrupt a lot, but I hope everyone still follows me. And then after that, we do one unstack of the, so that we are able to go back to the interrupt number 4. And then, you know, after that, which again, we turn down the active bit here and then change the base priority to whatever we had on the 4, which is the next priority. And after that, we unstack again, go back to the main, and then put the base priority back to 256 because there's no other immediate or any other interrupts required. And then the active bit is also turned down. Does this make sense so far? Okay. All right, perfect. Okay, so something, what we call like tail chaining, it's basically the same level or a lower priority level interrupts occurred while the CPU is handling an interrupt. And so what's going to happen on this case, right? Basically, it's going to be, let me just show you in graph, probably easier to look at. So basically, we're here, we have like a number 4 ongoing, and everything is stacked, and then we goes to the number 4, right? And then there's another interrupt raised, which is, which one is this? Yeah, number 1, which have the priority level of 10. So what happens here? Well, we don't, because it's have like a lower priority, we're not gonna, we're not gonna do much here. We just keep it on pending, and then we go ahead and finish the number 4. And after that, we don't do an unstack because it's essentially gonna be, you know, unstack everything and then restack everything back. A kind of, you know, wasting time here. So, but what we do is the base priority go back to 256 because previously it was not being interrupted because they have a lower priority. But that will be quickly changed to a number 10 because that pending of that lower priority interrupts still higher than this base priority. So that got changed and the active goes up, but we don't do another time of stacking and unstacking. And then we go into this interrupt process, interrupt subroutine calls, and then we finish it, and then we do one unstacking once for all, and go back to the main program. Still hanging good? Still with me? Okay, perfect. I see a lot of people nodding, so that's a good sign. Okay, next it's what they call like late arrivals. Basically, it's, so what happened if the interrupt occurred when you're doing the stacking? You remember like that little slope there on the hardware that take a little bit time, like the stacking and unstacking, right? So chances are something might happen during those small time gaps, right? So what do we do about that? Like what we call like late arrivals. Basically, this is what will happen. So while we're in the middle of, again, the number 4, the interrupt request number 4, we're in the middle of stacking, and then the number 3 happened because of reasons. And number 3 have a higher priority than the number 4. What are we going to do here? Do we do another stack? No, we don't do another stack because there is nothing to stack. It's currently still in that stack process of stacking the main program. So we just finish that stacking, and once the stacking is completed, basically the NVIC will look again at the pending here, if there are multiple pendings, and then chose the current highest priority ones to be executed. So essentially, although its cost, or like the main program was interrupted by the interrupt number 4, but because after the stacking, or during the stacking, something higher priority happened, once it's finished stacking, the processor will do the highest priority ones at that moment, instead of doing whatever triggers it, which is doing the number 3. And then, as you imagine, we will basically go ahead and do the number 3, and then all these active bits corresponding to it, the base priority 3, which is the priority of the request 3, and the pending bit of the number 4 is still there, just waiting to be executed, which then essentially turns into what we call the tail chaining, which is a lower priority ones followed immediately with the higher priority ones. So we just don't do another unstack. We keep everything there, and then finish the number 4. And then after we finish it, we do one unstack for all of them, and then set the active bit to low. We set the base priority back to 256, and everything just like nothing happened, except interrupts happened. But the main program still goes back to where it left over. Does that make sense to everyone? Any questions? Yes? Yes. Here, in this case, enable bits will always high, basically meaning they are all enabled and ready to file anytime if there's something happened in this case. Yeah. Any other questions? Yes?
When the program is stacking, is the enable chain off?
When the program stacking, it enable for the peripherals, you mean here?
When you stack the PC and the registers, is the enable chain off?
Sorry, can you say it one more time? When you what?
When you stack the PC, like during the procedure, is the enable other interrupts chain off? Interrupts.
I see. Yeah, the enables for the interrupts would be independent from the core, like when it does the stacking or non-stacking. Those bits are hardware registers that's only corresponding to each of these interrupts to see if they, if they're able to, if they're active, so to speak. They don't have to raise any flags, or they don't have to be active in terms that they have an interrupt request, but they're able to do an interrupt request if they want to, if that makes sense. Yes. Any other questions? Okay, perfect. We're doing great. So yeah, next is just some recaps that we talked about, like enable and disable interrupts, determine which interrupts are pending, and then how to clear them. And then in the end, we show you some diagrams of how do we do with different sets of priorities. Yeah, that's the end of the lecture. Please do remember to leave your worksheet at the end of the table up there. And yeah, everyone have a good rest of the day.
I